CLI and a cross-platform IDE for C and C++. Download now.
Hello, everyone. I have a declaration to make. No surprises, right? So the essence of a program is to create a specification of the system. That's what I claim. Our objective as programmers is to make sure that the decisions, the operations of the system are in the code, and it's the best form for them to be in. And I claim that the best programs are those that document the business logic and the behavior, the interfaces, the protocols, message exchanges, the data model, and the system options, all in code. Okay. Since early days of programming, we have been giving up our options and banging on data hiding and encapsulation and introducing strong type checks so that you can't just pass anything, restricting interfaces, expressing high-level intent, and getting more direct with the system behavior. And in many ways of expressing the intended behavior correctly, concisely, and without any vagueness, barring the occasional UP that we have in the language. And if you see what I mean, let's look at a simple, progression from how we went from assembly to today's state, where we went from go-tos to very high-level expressive languages. And it can get difficult to express intents clearly. This is where many languages and many language and library techniques come in play and alleviate this problem. We will check out several facilities in this discussion today, which allow us to express our intent at high level. In our discussion, we will also look at how beyond the language facilities, we can create our own declarative implementations. Okay? And we also draw inspirations from other languages out there. So let's see how close we can get to that. Before we get discussing the declarative style designs, I would like to ask you, and had it been an interactive session, I would have loved to solicit your answers as to what are some of the desirable qualities of software. At this point, I just would go ahead and note some of these which I have collected. They are not exhaustive, but your program needs to be functionally correct, complete, and as per specifications. It has to be consistent, safe, verifiable. It has to be testable and lawful and portable. And on the non-functional side, we need our things, our implementation to be efficient and high performant, also scalable. And safety appears here as well. Debuggability and monitorable, so that we know what's happening in the system and we are able to track the problems very quickly and easily. We want predictable behavior every time, and we want responsive softwares and reliable and available services. We want also our systems to be self-healing if possible and very, very usable. On the long term, as software developers, where this talk definitely touches upon is about maintenance and extendability of software, about reusability and flexible implementations, keeping things simple despite the domain complexity, not introducing any incidental complexity from our side, and intention revealing things and which are obvious and modular and non-repetitive. Okay, so essentially, we want to fall in the pit of success, where there is inertia to go out of the pit. The moment you move away from that center, you would be put back by gravity on the, at the right place in the center. Essentially, my way of putting it is, since we have more of the same everywhere, whether it is YouTube video suggestions or whether it is software development, you get more of the same. The system is inspired by itself and it keeps on growing in a way. So it is very important to be deliberate when building these, and for the spiral to be upward going rather than downward in a negative direction. And this is where declarative C++ comes in, because what I say is declarative C++ gives you so many of these qualities, which we have seen in the previous screen, the desirable ones. And, declarative style entails leaning on the type system, not using explicit control flow, and using more expressions and functional constructs like pure functions, pipelines, etc., composition, chained operations, etc. Now, we would like to work with values rather than having preferences and sharing. We would love to work with temporaries and exploit RAII to do its magic, as we are all fond of. You know, uh, Containing the complexity behind proven constructs so that you have constructs which express the high level intent and they have hidden behind them, any kind of complexity that there may be in the domain or the technical area. And going forward in a unidirectional flow is exactly what we want. Now, declarative style rocks, and we have used it in our team. And I'm giving this talk from my own experience of using this in our production systems, where as a result of these choices that we make, the declarative implementations, and coupled with good software engineering practices, we were able to drum roll. We were able to achieve just having one defect reported after our product was delivered from the field. So that is despite the low experience that the team members have, and the the technique that we did in the team to land in such a sweet spot was through declarative, coupled with right first time and shift left techniques and strong software engineering practices. Okay, so what does declarative style programming look like? Just before that, a bit about me. Uh, I'm in the Indian National Body at WG21, and I'm an architect working on cloud native products and libraries. And, you might find me speaking at company events or conferences and CPP India. I'm one of the core members. My interests are whatever, CI, DevOps, the kind of things that I was mentioning. And I love to go fast. On a personal note, we are, I love learning languages, but C++ remains to be my number one. I've done art with my children. I often do. And I bet you can't tell which one I made or mine and which one my 8-year-old made. And you'll find me going on treks. Okay. By the way, uh, if you're interested, we are hiring. So let me know. With that aside, let's quote Wikipedia. What is declarative? It's the style of building the structure and elements of a program which express the logic of computation without describing its control flow. So you're not willing to have the loops and the ifs and the jumps and the try catches, but you would like to just express the logic of the computation and let the compiler do it. And I said compiler, not ChatGPT. Okay, I would. I'm actually quoting also Andrei Alexandrescu from one of his talks. He mentioned this, that declarative is when you declare it, but actually don't use it, and it's a great way of seeing the declarative style. Okay. So we have compared a number of things about imperative and declarative. Imperative is when you give explicit instructions to go branch or take decisions and do actions, whereas declarative, you just declare your intent. Okay, so I'm not going to go through all of these here, but expressions is what we are looking for all the more. And looking outwards into what options we have on declarative, we have SQL, which is the poster child, I would say, of declarative programming. You just say what you want, from where, and what are your conditions to meet, and the implementation will get it for you. Networks often define bits and bytes of how a header on the wire should be. protocols define messages. This is the example of SIP, and it is based on the HTTP style. So HTTP is also similarly defined. Like you have a request, and request has a request line, followed by many headers, followed by a message body. You just say what it is like, right? It's great. You see regex. Regex defines what some text should look like, and it's so declarative. You see a REST API definition, and you see I've tried to highlight some of these lines where is the host, which is the port, uh, what is the body going to look like, what is the response going to look like. You define all of these things, in the REST API, and you let the code generation do the rest. Of course, you might want to put some business logic finally, but much of the infrastructure is just coming from this definition. Similarly, for the cloud deployment, you just say you want to run this image and at that version, and it should do TCP at which port, and that's it. You have a cloud service running. Very declarative are make and CMake, where you just say my standard is 17. My files are these.cpp. My binary is linking with these libraries. That's where you have to find the includes. So very, very declarative. And I'm sure by now, looking at all of this, we as C++ programmers are jealous, truly, really jealous, because we end up writing quite a lot of procedural logic. Okay, but we have a spread of choices, and it's up to us what we choose. And we don't have to be jealous. We just have to make the the declarative choices. Okay, so this is where in this talk we are going to look at how to have implementations which are easy to use correctly and difficult to use incorrectly, which exactly specify what the system is doing. We have declarative C++ language facilities to look at. This is not exhaustive. I have not updated the sub-bullets. We have declarative support from the C++ library. And then we look at some of our own practices which can help us, being declarative. Okay. So let's go and make some declarative choices. I remind you at this point that the C++ core guidelines defines the philosophy number 3 as express intent, where it says it is impossible to tell whether a code does the right thing about, whether the code is doing exactly what it is supposed to do. And an alternative formation is actually the gem, which is hidden in a note, which says, say what should be done rather than just how it should be done. Rather than providing control flow, you just express your intent. Very, very functional, I think you might be thinking, but it's not only the functional aspects that we will look at. We also look at structural aspects and other facilities which help us stay on track. So we want intentional revealing implementations and express ideas correctly. Now, if we look at looping, which started from the assembler, this is what an assembler loop looks like. The one on the left is from a thread in 2010. I don't know which processor that was. But on the right, we have a loop from Intel. And as you see, the condition is checked here, compare CX with 0. And if it is 0, you go out of the loop. Otherwise, you stay in the loop and you just keep on doing the operations. And this is how actual looping really started also. It started with gotos. You define a label and you can jump to it. But there was a problem. You could jump back to have a loop, but also you could jump forward. And that really made a spaghetti out of the code. And of course, we did not want this, right? So although the machine is doing these instructions and jumping around a bit, you don't want to do that. So what did we do? We gave up some of these jumping options. Okay, and we chose to have a loop which has a well-defined scope and it defines a condition, and you give up some options of jumping around. Okay, so let's look at this example. We will evolve this example. So we are just looking at a vector of streams. It's not difficult, it's just a vector of streams, and we want to go through them. We want to see that the occupancy is greater than 90%. Streams which are more than 90% full need to be flushed. So we flush them and we count statistics of how many times we did. Okay, so this is where we installed some sanity from the go-to, and it is much clearer. It is not moving around. But any issues at this point, we have a pre-increment which will skip the first item. That's an off by one error. We have an index, an I variable, which is staying alive much beyond the scope of where it should be. And we can do definitely much better than this. We want to restrict the scope of I. Now we have a for. And in the for, the I is only recognized within this loop. But it is better and more declarative. Now you actually know what the I is doing. It's going from 0 to the end of the string, right? But we have the post increment from the while loop correction, and it is incrementing the index 2 times. So this is one of the problems, and that's making a copy. And so we want to avoid these. We become more declarative by going to iterators. All we say is from begin to end of iterators. Now there is no index to meddle with. And we gave up the option of having the index or jumping around. We can still write the index loop, but we come to this more often. And now we can see that it is going from begin to end, right? But you have to read the loop in order to get what it is doing. No indexing issues, of course. Is everything okay? No. We have a begin of the streams, but end of X streams. This must be some global object, which you should avoid for sure. And we have this long type, which we can't pronounce. Anyway, so we have range for from C++11. And that's where now we even don't have an inadvertent copy, and we know that we are going from the beginning to the end without having to say it. Even though the assembly generated might be the same, but here our option or opportunity to go wrong is very, very less. Okay, good enough? No. We could actually use an algorithm. Why are we looping? The intent is not clear. And that's why I would suggest you use an algorithm from the library. And this is where you lean on find if. And now the code really says what it is doing. The iteration is separate from the business logic. You specify the condition on which you're finding. And then when you found something, you take the action. So the looping business, the technical aspect, it's not the important part. But defining your condition and doing the operations thereafter is the more important, right? And algorithms name and express the intent. Find versus plain looping tells you much more. And yes, this is actually just finding the first one and flushing the first one. This is different than the previous screens that we had. It was looking at all the streams which needed to be flushed, but you actually get the idea. Talking about algorithms, we have lots and lots of them, and we have quite a scheme. So you have modifying ones, iterating ones, you have rotate, which you might remember. You have transforming ones, you have generating ones and filling ones, you have remove, etc. So anyway, it's in the standard library since 98. And there is a scheme that if you have an underscore if, it will take a predicate rather than a value. If not, we'll do a negate. N will work on certain number of items, even if there are more in the container. And all of and none of is going to look at items in the container accordingly. So this also enables easy parallelism. Now, just by choosing algorithms, we can now parallelize our code. So this part of the code is still the same. We want to go from begin to end, and we want to flush the strings. But at this point, we are actually flushing in parallel just by specifying the execution policy. So you went declarative, you went and with the choice of an algorithm, and you are now able to uh, even get benefited by the option of parallelism that you have from the standard library, right? So just ask for it, and the compiler does. In the background, if you use par, a different thread will be spawned for every item, and it'll do its operation in the other thread. All that cleanup will happen. All of this for you, it's just mentioning the parallel algorithm. And we have unsequenced for using SIMD, and we have sequential if you want to still go explicitly specify that you want to go serially. Okay. Now you could also have custom policies for CUDA, OpenCL, and these can also be specified if you have the support and the libraries that they provide. And it just opens up by just declaring that I'm using CUDA, you could offload some work to the GPU. Okay, and new possibilities become a reality, and the functionality is segregated into small blocks. Now you're just mentioning what you want done, not the looping, not the checking of the alignment of memory, etc., etc. And this enables for longevity, and the code is much stable, and enables many more things. At this point, since we mentioned uh, you know parallelism, I would like to go through concurrency and parallelism facilities. If you consider this is also a similar loop where it is going through a 2-item array and pushing those back into a vector. Okay, it's going from begin to end of A and just doing a calculation and pushing the thing to a vector. And unfortunately, we have a parallel execution here, but we are using the same data structure, which is a big problem. Now, this is a data race, and you're into undefined behavior line. And attachment is the root of suffering, or sharing is the root of suffering. Okay. Now, what can we do about it? You want to explicitly exclude concurrent operations on the vector which is not ready, which is not thread safe by itself. So you just add a mutex, and you make sure that you lock it before you push back on it. So every thread will contend on that lock and will push an item to the vector only after it has acquired the lock. Now you have mutual exclusion, but and sanity is reinstated, but uh, no sharing. But at this point, there is no correlation between the guard and the pushback. So we'll come to this how we can have a construct which will make the mutex, which is guarding the vector, both of these inseparable. Okay. I think there's a slight problem with the order, so I'll just cover what we have on the slide. So we'll come back to the parallel problem. Now, if we have to send something in the concurrency world, either you share it by const or you share it by R value, so that you have relinquished the object onto the onto the other thread. And this actually makes sure that there is no contention. Often we use references just to share, just to not have to copy, but actually we don't have any intention of sharing. And this is a point which Dave Abraham always has often talked about. And so unidirectional flow is always preferred instead of sharing. And sharing const is still okay, but if some other thread is writing to it while this thread is just reading it, that again is a data race. So in order to not have a data race, you either share, send the R value, or you pass things by value. Values cannot be shared between threads, and they are local in nature. They are in the local scope, and it promotes unidirectional flow where the implementation just keeps on going in one direction. There is no return or back pointer, which is or a reference which is looking at things shared with other parts of the code. Talking about sharing, Amdahl's law is obligatory, and we pass. So you can only go so fast if you keep on sharing. Hence, I'm just repeating the point and making the point that pass values and ownership across, and let there be just one access to something, or in fact, no sharing and just local frame, uh, values to deal. And the slowdown of sharing is exponential. I was in a situation where I had 4 cores available to be allocated to my product, but I could not because it would just increase the contention. And we worked to improve that, but was a sorry state to be in, that we have the hardware but you cannot use it. So this is a very real thing, and so not to share and to keep working with values is a very important aspect of declarative programming. Okay, so now coming back to the problem of the vector and the mutex, an object and the mutex. I've seen this implementation from libcs guarded. This is copper spice library, uh, and it presents a number of options. I'm just showing you one of those here. If you have something called as a guarded object, you would have a mutex and the object together uh, in one place in this construct, and they are both private, so you cannot access it. Okay, you can construct it, you can pass all the parameters that the object needs to construct itself, and have a mutex, or decide what kind of mutex you want. Maybe you want a shared mutex, maybe you want an exclusive mutex, unique lock. So you based on that, you can mention these things. Now what this does is it creates its internal, it will not allow access, because as we saw, I'll just go back to the previous screen. The object is private and the mutex is guarding it. There is no way to get to the private data unless you are a friend, and this class will not let you be a friend. Okay, so it just manages and brilliantly uses the unique pointer and the custom deleter functionality of the unique pointer. So it just defined a unique pointer handle for the T. This is the T that you hold. It's not really a T which is allocated on the heap somewhere, and you want to really call, new and delete on it. It's just the T which you hold in this class. So you give a pointer to it with this deleter, and the one job that this deleter has is to unlock. Very RAI. So the only way to get this handle is by calling lock. Okay, and please note, if you have a mutable object, when you call lock, you get a mutable handle back. If you have a const object, this guarded object, guarded T, is mutable, is constant, then you can only get a const handle back. And overloading makes the code similar, and you just call lock. Now all you have to do is, for example, in this case, we have the guarded vector to which we are passing all the parameters that we need to pass to the vector, and the vector is initialized inside it. And as you see here, when you call lock, you are able to use the object, and this is with a constant ref. So this one is able to call a const function on this because it actually got a const reference of it. If, on the other hand, you call lock on it, if you had the const ref, and you call lock on it, and now you try to call insert, this will just not compile. So if you do not have the rights to actually use the object, we have converted what we had as a runtime error and a data race problem into something which can be a compile time, quarter compile time. So if you just use it through the guarded interface, this is what is guaranteed. If you cannot have access to read-write access to it, you cannot call read-write functions on the object. Okay. Similarly, if you had a non-const, a read-write handle to the access to this object, your lock will give you the allow you to push back and edit the vector. So this is a strong facility which is beautifully just using, so this guy lock is returning the unique pointer, and you can use the pointer till as long as you want, and once that goes out of scope, all the unlocking business is also automatic. So you don't have to say anything or mention a control flow or explicitly call unlock. None of that. The scope will take care of it, and it's a beautiful use of unique pointer and its custom deleter. And what I would say is, we have done that in our production system, that we have overloaded the operator arrow, the dereference operator, to actually lock. And it's clean. It's a good way to work. And this code in the previous slide had lock here. And then you could use the size on the vector that you got after the lock. But here, just by doing the arrow, operators are beautiful. They let you express what you want to do directly. But beware that every time you call arrow, you are actually doing a lock. And at the end of that line, you would do unlock because you are not held on to this reference, to this unique pointer which you got. Okay. Once you are in control of that and you are cognizant of that, you are not going to have lots of contention on the lock. You can hold on to the pointer if you want to do a number of operations on it till as long as you want. Once you set that to null PTR, you're just good. It will be unlocked, or if it goes out of scope. But this is a very convenient way of using it, as far as just the little part that you appreciate that it is giving you this facility. So if you think you might not have much control on how the object may be used, then maybe you don't want to implement this operator for your object. Okay. And at this point, again, another very intent expressive construct, the reducing this, which has come in C++23. This allows you to implement functions in a class where this pointer itself is templated. So you will definitely pass that the same this pointer that the class should get. You don't accidentally get, because this is done by the compiler. The first parameter of any function is the this pointer. And it's internally so in the implementation, we don't have any access to it. But this feature is allowing us to define, just specify that here as with this qualification, and you can use the template and the the reference specification of the template, which can bind to any L value, R value, const L value, or a const R value. Okay, and this self will be that type. What that means is, if self, when you call this operator, if self was a non-const, a read-write object, then this would be an L value reference to this. And this lock will give you a L value, a read-write access to the object which you're holding inside the garden. Whereas if you had a const reference to this, or a const this, you can only call the const invocation of lock. See, beautifully overloading plus this feature is making sure that the generated instance of this template is going to be correct, and you just have to declare this one line in a very optimal way. Just have this one implementation which can factor for all the possibilities of const, non-const, R value, or L value. If you wanted to do something like, you know, in case of R value, you wanted to actually return the object by, by an R value reference, you could actually do it. So more bang for every line of code that you write. All right. In yesterday's session, Dave Rowland presented about this. This synchronized value was I have not mentioned the paper here, but this paper was presented to WG21 about synchronized value. This is pretty much the guarded object that I have presented in front of you. But I think there are some issues with it. We have happily used it, but I guess uh, I don't remember exactly what Dave mentioned was the problem with this, but looks like it has not gone through or not getting traction in WG21. Okay. So as far as sharing is concerned, you look out for data sharing, and when using parallel algorithms, just be doubly careful that you're not accessing, you're not causing a data race. Make invalid operations like data races impossible by having the construct that we just discussed. RAII magic takes care of locks and unlocking. It's beautiful. And const versus non-constant access is ensured on your type. With deducing this, you just wrote something once, and the compiler used it to stamp out 4 different kinds of possible functions and exploit the type system. It really works. Okay, so we just discussed the operator dereference, and I would like to take the opportunity to discuss about operators in general. In C++20, we got the 3-way comparison operator, which again is so declarative. You just put this line in your type, and it will make sure that in order of member definition, of member declaration, the members will be compared between 2 objects of the same type. And all the operators like less than, equals, greater than, less than equals, greater than equals will be stamped out by this implementation should they be needed. If they are used somewhere, these will be stamped out just by declaring this line. So you're calling upon the compiler to write an operator. For example, let's take the example of an equals. So an equal stamped out by this declared line would actually compare the 2 IPs first. And if they are still same, the ports will be compared. And if the ports are also same, then the protocol will be compared, and that would decide the return of the bool return. Sorry, it's not a bool return. That would decide the return of this operator. And whatever it returns an ordering object, and that is convertible into bool. So this code at the bottom is thus possible. You have a destination D1 where you are defining an IP, port, and protocol. You make a copy, and they are bound to be equal, and that operator actually exists because you declared this. Okay, there was some silent breakage of some code due to return type not explicitly being bool, and also due to implicit type conversions of types. But if you don't have uh, example existing classes on which you are defining, I think you might be good. So just I'm making you aware that there could be some problems or breakages if you define this in C++20. There could be a breakage, but other than that, if you happen to hit that particular case, apart from that, this one is just a boon. You do not. I have done this myself, that I have defined all the possible operators and gone wrong in copy pasting, etc., and learned it the hard way. Okay, so you just don't have to do the donkey work anymore. Okay. You may have observed that on the previous screen, I have used the IP address like this. These user-defined literals were a possibility starting C++11, and it allowed you to define an operator of your, like with whatever name you want to give it, In this case, I've just given it an IP. It will take a string and a size. I think it should be a const char pointer. And it would just parse the string and create whatever object it is supposed to return. So this is an operator underscore IP, which can take a string and it stamps out a real IP address. Okay. And my to IP address is implementation is actually doing from string exactly what I'm doing here on the right hand side. So this operator is actually creating an IP address object from that string. It'll have the same value. The second line is an IPv6 address, easy peasy. That is also similar. You can now go on to define lots of different objects and convenient ways of dealing with this. Maybe you have a configuration where you're configuring. Sorry, you might have a test where you want to check post port. Somewhere returned by some functional block is correct or not. You can be very quick and explicit in mentioning this here. Okay, I had const expr and all those things are possible with this operator. I have removed those for slide purposes here, but you can go where you want. You can define something like a URL. So you can have a string underscore URL, and that will stamp out a URL. Your imagination is how far you can go. You can even do a JSON. At this point, I would just like to show you what Hannah did with this. The CTRE library that she has for regular expressions is actually dealing with strings at compile time with the operator underscore pre. This was how she presented in 2017 at CPPCon. I think she's gone ahead to do better than this in C++20. Now, std string can be in the template, non-template type argument list. And so that library is actually benefiting by that. But here, as you see, it is actually stamping out the whole regular expression. What we have on the top here, you see, it is the type which is stamped out by this pre operator is exactly what by hand is written here. And these two are equivalent. Like begin and go to any character, then there has to be any of the characters A, B, or C followed by XYZ or optionally XYZ. And so it's a select. And so you see, you can really do a lot of magic by doing this. And all this makes it just declarative. We saw the regex as a declarative option or declarative construct. We do have it in C++ at compile time. And I guess in this presentation, she showed that all this regex was compiling down to just 64 instructions, which was super duper bumper. Like, I was in love with it when I heard it. A very short talk, and I encourage you to go and check this. So, overloading operators make generic implementation possible. You can use the pointers with the arrows and okay, I've mentioned it here. You can dereference operators and all pointer-like things by the dereference operator. All your mathematical types, your matrices, physical quantities, and numeric types and vectors, and so numeric things can be benefited by operator overloads. We also have string, which is overloading the plus. So it's not only restricted to numeric, although the opportunity to have meaningful, association, a good meaning associated with the operator is much less. Like what would a department plus department do? So it's not much of a in many contexts, in many domains, it's not much of a help. But if it means something, if it can be mathematical or clear, this facility really helps you define implementations which just define the operator, and it just works generically with many types. And all the functionality is behind the operator, like the one that we had for the regular expression, etc. and it definitely enables expressiveness. You can really see the string meaning something. You're not behind an IP object where you're defining all the 4 octets explicitly, or you're choosing which IP you're defining, etc. So a very declarative way of doing things. Okay. Next functional aspect is parameter packs. Uh, this we have had in since C++11, and in C++17 we got something called as fold expressions, where an operator or an operation could be applied to all the arguments that you pass as a parameter pack. Here we have this function called as log, which is taking any number of arguments, and these are just output onto, let's say, cout in this case. And this code would expand into, let's say you passed 5 arguments here, it would expand into cout of the first, and followed by the second, followed by the third, fourth, fifth, and finally /n. So this is what the the fold expressions actually got you. And many of you might be working with C++17 already. So you can take the opportunity and be benefited by this very, very declarative way of having the operations. We have used this in our implementations where, without any type conversion, you often see logging where the types that you want to log, the text that you want to log, you first do it on a string stream, and then you are able to pass it to a log API. You don't want conversions when you pass it to an API. You actually want the types to directly write onto stdout and not into intermediate string concatenations, etc. All of this is just wasteful use of your resources. And this is what prevents that. It just will concatenate the time followed by the service name, followed by your message, followed by any debug information. If these passed objects define the operator indirection, this one, the cout operator, then your object, the contents will be printed. Okay, very beautiful. And if you have 2 log statements, one passing 4 parameters, the other passing only 2, there will be 2 instances stamped out. There will be no ambiguity or no runtime overhead selecting which one is to be invoked, and specifically type safe manner invocation will happen for the correct function. Okay, and you have more folds, so you can have so as you see here, this one was expanding. This is an example from CPP reference. This one is expanding the various values that are passed to all as it is defined here. All it does is does an AND on all of this. And this is what it does. The first true and the second true are ANDed. The result is then ANDed with the third one, and their result is then ANDed with the fourth one. Okay. And as you see here, any short circuiting is also enabled by by having this kind of a logic. Just last month, no, we are still in Feb, sorry. So this month in WG21 for C++26, there was a paper which Herb presented, and it was accepted for C++26 that, less than equals operator for fold operations are meaningless, and they will be excluded from being valid expressions. Okay, because you can't do anything meaningful by saying A less than equals B less than equals C less than equals D. I don't know what it means. And it was really ambiguous. So that got to go ahead for C++26 just this month. Okay. Talking more about parameter packs. If you have a parameter pack, as we have here, we have many T's passed on as values. C++26 or 23. This was C++23, I think. So C++23 allows you to reference items in the parameter pack by simple indexing like this. If you have a T ... and indexed with 0, you are actually picking up the first one. So as you see, this function is called as first. So if you pass it many parameters, it'll give back the first value. This one is last. If you pass it many parameters, it'll give back the size of values -1 at that position, the item at that position. Obviously, the type is also the type at that position. So if you have a lot of parameter packs, uh, now you don't have to go down the route of having index sequence, make index sequence, which gives you integer sequence, and you have to do all that trickery, just the long route. All of that is now something that the compiler itself provides. And you can just say, I want this. The first item, the nth item, it's just like an array. As you see here, the first item out of 1, 2, 3, 4, 5 is 1. The last item out of 1, 2, 3, 4, 5 is 5. So if you add the first and the last, expectedly you get 6. Okay? This is just right there, beautifully, very easily done. So it makes life easy if you're handling parameter packs. So C++ is getting feature packed. Working with parameter packs is so much easier, and folds enable great expressivity of what you want to do. Okay. And compiler is doing it all correctly for you in the best possible way. So say bye-bye to long-wounded ways of doing those things. Such a relief that we got this. No questions I see at this point. I'll proceed. So coming back to our problem of the streams, we had this flush streams where we were doing it for all the streams, but actually we wanted to do it conditionally. And there is no algorithm in the algorithm's header which can express that. What we want to do is for each if. So we want to go ahead, not stop at the first one that we find. And we don't want to copy or remove copy. That's not what we want to do. We just want to process and run an action on all the items in a container. We have transform, which will not stop and do it on all. We have find if, which will find the first one, and you have to redo the find thereafter. So it becomes a loop of loop, and it's not healthy. So the best way is to write your own custom algorithm, and which is exactly what we have here. I've implemented something called as for each if, which goes for each items in the stream. Do this action if, for each, do this action if this condition is met. And this has got the things back into declarative land where we don't have to write the if else. You remember there was an if after a find where if we find it, we do an action. It is still saying, what jumps to make and what checks to do. Rather than that, we have here an algorithm which is clearly stating what the intention is. And the name reads and says exactly what it would do. And you can happily just use it and express your intent. Functions and lambdas enable implementation in terms of expressions, and separating decisions from the actions is very explicit. There is no confusion as to which part is the decision, this one, and which part is the action, that one. And it is clear. Or is it? Is it that readable? Let me just help it by just giving things names. Although defined in local scope, this name still makes clear what the intent is. Is full tells you whether a stream is full. Do flush tells you what it'll do. And now your algorithm actually says it doesn't even have to be in different lines. From beginning to end of the streams, just do flush if it is full. Okay, so we are now expressing in terms of expressions rather than actually control flow or jumps. And naming, although hard, something that I would encourage at all times. Of course, we had a hard coding for the number 90, maybe 90%. for what full means. So you should not hard code. We have the G threshold here, which is really now carrying the value. And now the value can change. But now your code depends on this global. And what if the global changes? It looks like a parameter that would not usually change. But what if it changes? Now your function is not having predictable performance. It depends on this external G threshold, which we can't give guarantees, can't, assume things about. And I don't know if there's a guarantee that will not change. Is it a const? If it is, then it's a different story. But if it is not, that's a problem. More often than not, I see these kind of thresholds coming from a configuration, and so they may or may not be uh, a constant, depending on whether you want hot, while running, you want these things to be changeable or not. And so now your implementation does not actually have the same performance for the same inputs at all times. This global is changing its behavior. Which items it will select will be different. Okay. So move towards purity. Pure functions are those functions which depend only on the inputs given to it. So these functions, in our case, this function will only work with streams and the threshold which is passed to it. It may come from a global, but it's not the assumption that this implementation is making. If you pass it externally, now you have a pure function. And this actually enables a lot more composability by passing different values at different times, making testing very easy. But really, the intent is much more clear, is the biggest gain out of all of these reasons which I'm giving. Now, the threshold is passed as a parameter. It is then checked. It is then used to do the check. And now again, based on the value that you passed, you may get a different behavior for one value of streams and threshold combination, you will always have the same behavior. And this is a very important aspect for composable operations, where you want to put one after the other, and sometimes you may put it in the wrong or in the different order, but you would like idempotency, or you would like the same behavior irrespective of the order in which the operations are done. Okay, so it's pure functions is a very good way to keep things sane. Now all you need to do is to understand the local frame. Nothing else in the universe is of significance at this point, and your code is very, very understandable by looking at just the 4 or 5 lines that you have here. Okay, so pure versus impure, I mentioned a few points. Just that if you make it pure, local reasoning truly applies, and it's easy, enables composition. I have mentioned about this. It'll be there in the slides. Now, this was the pure functions slide that we had from before. Now, this is a very similar function, but it is doing something very different. This is dump streams, and dump streams is looking for something for error streams if the status is error, and it wants to do a dump rather than do a flush like the previous implementation was doing. But as you see, the same algorithm, the same construct is now allowing for this functionality also to be realized. Okay, so having generic constructs let you implement much more than what you started with. If you see the algorithm implementation for the for each if, you will see it takes 2 iterators, B, and E before begin and end, and the action and the predicate. This is where the loop is hidden, and none of the rest of the code now needs to have a loop where it's all behind this function. So what decisions have to be taken, they have to be taken. Some of the decisions we'll discuss how we can move them to compile time or initialization time. But some looping, for example, it is depending on the status right now. So it has to be iterated over. But all of that is all, hidden behind this function. So there's a loop which goes from begin to end, and it picks the item and invokes the predicate. If the predicate is true, then the action is taken. Okay, std invoke was a functionality that we got in C++17. And if you pass to it any kind of function, it is all acceptable. So, now new use cases were allowed because we could actually take just anything in these parameters. Okay. But what can we pass onto this one? Passing templates is like you could pass anything. Do you even know what can and what should and should not be passed? So we have that problem. But before that, I would like to mention that since we added this algorithm, somebody is really happy. It is great parental advice to identify opportunities of algorithms that you have in your code and use the standard library once or build them for once so that you can have a vocabulary of operations that is possible and it is reusable thereafter also. Just you call upon the same construct. Just ask for the same thing to be done. Okay. So going back to our implementation, this was the exact function that we had on the previous screen. And here, like I just mentioned, templates are the void pointers of C++. You could just pass anything, right? So how do we say what is expected out of these types? What are we going to do inside our functions? If you try to read standard library, you might have to jump around quite a lot in order to just understand what it is doing. And to add to it, when you have passed a wrong construct or an incorrect type, it will just penalize you with a wall of errors, right? So how to get around that? Now, our expectations are implicit. They are not made explicit. Can we do that? Yes, I would add these constraints, which we got in C++20, in order to constrain the algorithms, constrain the usage of this function. So input IT is a template. What is required of it? What we require it to be able to do is that it should model the input iterator trait or the concept of input iterator, which is that of being able to dereference and increment, right? So that's what an iterator would do. There is an official definition of this. I'll let you check that on CPP reference. But input iterator essentially has a value type. It points to something. It can be incremented. It can be matched against an end, and there are some such expectations out of the input iterator. And once you have that, you know that this condition is true. If you don't, the compiler will for sure evaluate this at the time of the use of this function, because this function has declared that it needs an input iterator. So whenever you pass something, this is picked up and matched at compile time. It is evaluated at compile time. This condition would evaluate to finally reduce to a bool, which says yes or no. So if a type models the input iterator, this will be true or not, and that input iterator would allow next checks to happen, or else the compiler will now give you a very reasonable error saying the type that you're passing, that IT type, is not what I expect. It does not it does not meet these requirements where, let's say, it should be dereferenceable or it should be incrementable, pre-incrementable, something like this. Similarly, we have a unary invocable. So there is a concept called as invocable, where a function f is invocable with certain types. Let's say it takes 3 parameters. So int, bool, and string. So if it is invocable with that trait would say true. But at this point, we want the invocation not on the input iterator, but we want an indirect invocation. We want what iterator is pointing to be passed on to the action. We want the element in the container to be passed on to the action. That's why we are using the indirectly unary invocable. So we are just passing one item to it, which is the indirect item which iterator is pointing to. And if this construct is valid as per this concept, then your the data that you have passed, the action that you have passed is okay, or else it's not. Similarly for predicate, it is indirect unary predicate. A predicate must return a bool or something that is convertible to a bool. And so that's the definition of a predicate. And if the predicate actually returns a bool or a bool convertible data, a bool convertible type, if you pass the value pointed by input iterator, then that's perfect. And so with this, we have just made clear what our expectations are from somebody who's using this. Like I told you, the intention of our code is to be a specification of the implementation or of the business domain or the technical domain. In this case, it's an algorithm, it's a technical construct which is making clear how it can be used and what else is not possible. All right. So, and all this is compile time checked. So once this is checked, the invocation is obviously correct. And now it's on to the runtime to do the most efficient operations possible. All right. So with concepts, it's also possible to overload things. I just gave a silly example here. There's a is power of 2 function, which expects an unsigned integer. Can this be uint 8? Yes. Can this be uint 32? Yes. But it can't be anything other than an unsigned integer. So we have 2 functions defined here. One is taking a concept. So it's taking an auto. It's taking any type, but there is a qualification to the auto. This is the terse syntax with concepts. So it takes a qualification to auto, and it makes sure that the end that you're passing here is definitely an unsigned integer. And once that is the case, it knows how to do its thing, and it will return the answer. If it is any other type, so this is the same signature with one item being passed, not the same, but an overload. For anything else, there is false, not MasterCard. So this concept lets you have overloads based on which concept is matching. So based on the use, when somebody calls this with a uint 8, this code will invoke the first function. If it is called with anything else, in this case, it's not a very smart choice, but I just wanted to show a point here that overloads are possible with with concepts. Okay, so going generic, Purity really enables for predictable, correct, and testable behavior. Go for functions and lambdas, they make your code full of expressions rather than statements. Generic implementations build a vocabulary of constructs. So for each if now in your code base is a generic way of doing something, and anywhere else you might need it, you have a proven way with lots of tests. You can have a very stable construct, and now wherever else you use, all you have to worry about that is whether your condition is correct and whether the action you want to take is correct, and everything else is taken care of by the generic implementation. Okay, and it can enable novel uses also. Concepts and constraints really help you eliminate errors at compile time and not have a binary till you have it right. And once you have it, it's great because you're passing one-liner lambdas to it, your code is visibly, when you inspect, you know that it works and it will work. Of course, you'll have a few tests to prove things. And the implementation at the caller site is not full of uh, explicit flow control. It's just stating what it is doing, which is really a proven functionality. Okay. Now, like I just mentioned right now, you just focus on high level decisions and actions. So the decision at your end for flush streams was to look for occupancy and carry out a flush action, whereas the one for dump streams was to look for errored streams and carry out a dump. Okay. And visibly inspecting these two functions should work if just this line is correct, which is looking very, very trivial, and if this line is correct, which is also looking trivial. Okay. These are the differences between the two. Okay, so you do not take low-level decisions. Now you are actually staying at high-level decisions. All right. So with all this algorithm business, we are now entering into ranges land, where this is what we had so far, where we had the flush streams defined is full and do flush operations. And now we will try to use ranges to do the same thing rather than using algorithms. As we saw, algorithms, we were having 105 plus algorithms, but we were not able to compose them together. We had to write a new algorithm. We had a condition or uh, a scenario which we could not represent using algorithms. If had you done like we discussed, had we gone down the route of doing find if and then doing an action, then again looping back to find if, then that would be a combination which would need either temporaries or lots of still defining lots of control flow, and that would not be a beneficial exercise or good use of our time. Ranges, what we got in C++20 allow us to express things very clearly. So what are full streams? Full streams are those streams which are full. And what's the definition? Yeah, you gave your definition. Okay, I've shortened the name here, threshold. So you want a filter to happen. This is just a view of what the streams have. Okay, and you defined a pipeline here using the pipe operator. But that's about it. This is just a definition of pipes, like pipes connecting to each other, but no flow yet through them. There's just a definition of a construct. On the streams, you would like to filter based on is full. And then now you want to go through all of them and do flush. And as expected, from streams, the whole container will be iterated over, and only those items which the filter will pass will be taken to the next state. Which means those are the only items which for each will see until the filter is approving of a value. You will go to the next stream in this container, but not pass the filter, which means you will not go through this for each, the next step of for each. And now you are doing do flush on only those items which have met. So this is so very declarative that the intention is very clear. Now, passing begin and end everywhere was actually a missing abstraction in the standard library. It was the representation of a range which was missing. Range is defined as something that has a begin and end. And now you could pass a range here. Like this streams is a range. It has a begin and end. And you made this pipeline that has a begin and end, and that you are passing to for each. And now that is able to iterate over that range, whatever that is, the pipeline. So water flows through the pipeline here. because you have a range here, and it's just a lazy range. Be lazy, it just works. uh, and and ranges was the missing abstraction. So if you have a function, let's say you're passing 7 items to it, you have to stop and think, are there any missing abstractions in your implementations which you would like to make slightly higher level constructs for? For example, I have you know a switching case where let's say the version of data is switching. Okay, the version of data is switching. There is a pre-version, there is a date, and the post-version. If you pass these 3 parameters together to a function just to evaluate whether this data is to be interpreted in a certain way or not, or to parse the data, you have now passed on 4, at least four items to that function. Whereas really, what you have is a specification of a switch config of a switch, let's say a switch configuration or a switch setting, where that setting has a pre, post, and a time, and that setting is entirely used in all operations which are looking at it. For sure, there's no point in passing these 3 items, keeping them separate also. Even if it is coming through configuration, it can be right from the onset of the implementation. All of that can be just one object with 3 items. It's no cost. It's just the same as 3 explicit items kept without any meaning. Like we saw in the concurrency case where the guarded was keeping the T and its mutex together. This is what you ought to do in this case. So we did that, and the interface was very, very explicit and very clear to read and understand uh, that it was taking a switch configuration or a switch setting, and it was looking at the data. Now, data could be a pointer and a length. And as you know, in C++20, we got span, which can put that together. Because unfortunately, thanks to C heritage, we in C++, when you pass a pointer, it loses the knowledge of how many items are there in it. And the called frame does not know how many items to look at. It can only assume how many, or it can look for a special sentinel like we look for /0 in a string. It's very unfortunate that we have to do that. Whereas something that Diano was trying to push in the 90s also or 80s, something called as fat pointers, is the span object that we got in C++20. And all languages, Go, Rust, Java, have something called as splice or span. And it's just a helpful construct to have a pointer and the length together. So that also is a missing abstraction. If you are taking, let's say, a pointer and a length which are associated, you would actually should consider passing a span, which gave us a lot of stability, because span is just like a container. It has a begin and end, and you can't go wrong with pointer mathematics if you're not doing it, right? So be lazy and be declarative. Just change the operations. I've shown you only one, but there can be another pipe at the end of this, and another pipe, and another pipe. Okay. And not only filter, but you can also do something called as transform. That also is just defining the pipes and joining them together, not flowing anything through it. The flow happens when you actually loop through it. It's all lazy in the ranges library. Okay. Be lazy. I can say one more time. And these past functions can, these past functions and lambdas can even be member functions or function pointers or std function. As you know, any of these is okay. Okay, and I've shown you both styles of algorithm style and factory and adapter style, which is through pipes, and this is the algorithm style. Okay, we also have in C++23 something called as ranges 2. Let's see, look at a problem where from a string, I want to return all the words which are greater than 5 characters in length. Okay. So words longer than 5. Okay. You pass a text to it. Now, there is a view called as the split. So on the text is a container, the string is a container, it has begin and end, and it is a container of characters. So you can use any of the ranges and the views on it. Your split is the algorithm that you're using. It gives you a range of range. So from the original range, it gives you a sub range, okay, for the split that it has done. So it looks for space and it splits the text based on that. When that range is returned, it's actually a range. So I'm taking that as an R. And I want to see that the size of the range, which is begin to end, is at least greater than 5 characters. At least, okay, not at least, it is greater than 5 characters. Okay, if that is the case, only then I want to go forward, or else look at the next token, next token, next token. Okay, and then there is a transform which I want to do on it, where I actually convert the word into a real string, and that string is what get passed on to something called as ranges 2. Now this is a terminator of pipelines, and this when you add and when you invoke here, you have actually called it. Okay, so which means it is now, because of that function call, it is now looped over the entire pipeline which you just built till before that character. And when you invoked it, it is like an immediately invoked lambda. You define a lambda and at the end you immediately invoke it. It has its uses, and so the 2 is a termination to a pipeline. You cannot continue this pipeline further. The pipe operator will not work. All this is at compile time, and thanks to the abstractions in the standard library. And the type of the vector, see, you don't define, is starting C++17. I don't know if you know, you can just have a std vector v and open brace pass 1, 2, 3, 4, 5 to it. And you have not set the template type here, and that is deduced by the past initializer list. Okay, and this is a valid code in starting C++17. Similarly here, you don't have to say what type is the vector going to hold. It is the type which is passed to it from the previous stage of the pipeline, and that in case we just created the string and passed. And so we have lots of these data flowing temporaries being passed around without any copies, etc. And a very efficient code is finally churned out to create this vector of only those words which are of size 5 or not. You could have created a string view here, which would prevent a copy. But if you're not sure whether the string view will start referring to memory, which is going out of scope, then you might as well you will have to make a copy of the string. Anyway, this is a slide example. And no raw loops. So that's your loop. As you see, there is no begin or end of the loop. All you have done is just chained operations. And it is very clear that these are small operations which let you do the big functionality of splitting the string and doing everything that you want. And this is what is returned by the function. It's just became almost it is one line full of expressions with just a few operations. Range adapters let you see the range in a certain way. Okay, so if you have a map, you can look at only the keys of the map, and that's just a view. You're just iterating the map, but you're only interested in the keys. Okay, similarly, you may have values. Okay, so let's look at that. So even if you have a tuple, remember previous screen we had a map which has a pair which has keys and values. But if you have a tuple with 3 items, what do? The same keys and values implementation is also available for this implementation. So for this vector, which has 3 things, string, double, and bool, you actually can go through only the keys. Even in this case, just calling it keys implies that you are looking at the first item in the tuple, because a pair is a tuple of 2 items. It's just like a tuple of 2 items. If you look at values, you are looking at the second item in the tuple. So you're going through the items of the vector, but just looking at the second item. And if you had to say a different position, you could just use the elements view. And by saying element number 2, at compile time, you have decided what you want to look at. So that's the bool which you're seeing here. Okay, so very convenient. Range algorithms also, do the, give you algorithm like callables, and you can just call, like min max is there in algorithms, it's there in ranges also. And this actually this internally might be doing whatever lazily, but finally it is a function that you have called, so it gives you the return type, the actual values. Just like algorithms, ranges is also full of options, chunks, slide. You can join. So there are many of these operations which you can do. It has a ranges of options. Okay, I think there are questions which I'll switch to right now. Regarding for each if, will this function work for streams? Actually, these objects are not copy constructible or copy assignable. Okay, there is a slide number at the bottom. It'll be great if we can look at that, but perhaps this question maybe we can look at in the gather town, if that's okay. If it is copying, no. So if you're referring to the loop inside the for each if, it is actually taking was I taking a reference? No, I should not assume that. Okay, I'll have to see. I think you have a point. Marcin, thank you for your question. I think you have a point. I don't know if I made a copy. Okay, I think you have qualified your question with the next question. So value at B is a copy. Auto S equals value at B is the line that Marcin is referring to. And you're right, this is a copy construction. And I was supposed to mention at that point that this is not real implementation, because I guess in real implementation, you can just dereference the iterator and you would get the same one. But if you have to invoke it 2 times, I'm not sure what the standard library does. I know there's a lot of noise because the filter view might dereference the iterator multiple times, and that is a problem in many cases. So the standard library is a very smart piece of work. I guess we all should go back and find out how it does 2 invocations, the predicate and the action. Allow instruction of namespace should be stdv, std views. Okay, yeah. Okay, so we have optional, where you might have a lot of code which is going from which is going step by step, and there's a huge possibility of failures. But these, you have to check at every stage, at every step, and take a call whether you want to proceed or not. Now, it is too much of checking. If it is returning an std optional, you might as well use the monadic interface, which we got in C++23. And the same operation, this is from the paper. So from the paper which introduced the monadic operations, you can actually chain operations just like we chained them in the ranges. Okay, so this is another way of chaining operations. But as you know, optional just says whether it has something or it doesn't have. So it does not give you the error in case you found an error. It's just would say, I don't have the thing. Okay. For more functional aspects and these things, and for std expected, just look at Jonathan Mueller's Talk Tomorrow. Okay, we also got coroutines and generators. So coroutines let you have resumable functions, and you can yield early from the function, and the whole context of the function, the iteration, the loop, the check, uh, the execution position will be kept by the compiler. So much the compiler is doing uh, by just yielding at this point, and when you invoke this function again, it will come again to loop or to do the operations next. Okay. So if you have a tree like this, and if you just call the traverse in order, you would get these operations yielded. And as you see, this is returning an std generator, which is a C++23 construct. You got the coroutines in C++20, but the generators you got in C++23. And this lets you make potentially an infinite range with the generator. Okay, it is very tedious to work with coroutines right now. I was expecting some library support, but I don't see much movement. Okay, attributes. If you put a no discard, the compiler will help you with the information that you did not handle the return type of this function. So you might as well it will be a compiler warning, and you can stop and pay attention to it. If you have no return, this will help optimizations to happen if you define a function as a no return function. And if you have deprecated, you can actually even say why it is deprecated. Okay. And this will give you a warning if you use this in your code. Okay, the compiler again is helping. Delete also got a reason. So you can say the reason why you're deleting a certain special function. Okay, for example, in this case, there is a move only function which is deleting copy constructors, and because it is expensive, so you can just say that. Okay, relying on strong types, you can convert for once at initialization time something like this. When you're starting your system, if you look at the configuration, it is a passed value, but after you pass the value, you can now run the system with a templated value by just doing a switch once, and your entire system, now the service is created in flavor 2, and all the objects like a factory would do would be constructed with the types of flavor 2. CTAD also helps you with types, where if you create a container with begin and end iterators, you actually don't mean to have a container of iterators. What you want is the container of values of what the iterators is uh, holding. And so this is the way you say it, that last line, additional deduction guide you can provide. So when you have an iterator, if it is obeying iterator states, then actually it is a container of the value type. And this is how this by just declaring that part, the instantiated type is very different than just the what you see being passed. Okay, if you create strong types, even if this type is the same as the message, but if you have a strong wrapper around it which makes a different type out of the message, uh, you now have an overload, and there is no confusion as to whether you're taking encrypted or the message. If you want to disallow message, you can just switch to using encrypted message. And the only way you could get an encrypted message is because encrypted is a private type of the let's say the stream. And so if you the only way to get it is by calling encrypt. So that's the way you would get it. Okay, and use R values to pass. And finally, if you want to do something always on leaving the scope, like submitting statistics to a global statistics, so you are being efficient, you are locally calculating the things, but you want to always submit this. Now, if you throw an exception in the middle, that last line will not execute. If you have an early return, it will not happen. Classic problem with C memory leaks, right? And we have solved this by creating an RAI construct. If you create a scope exit which to which you give a function which can be invoked at its destructor. Now, howsoever this function returns, this object will go out of scope, and the submission of the statistics will definitely happen. So this is from Kevin Henny's keynote from yesterday. He notes very correctly that the hard parts get all our attention and we often get it right. But the small parts are where the bugs are hiding. And the standard is doing exactly that by alleviating all your problems by providing these good constructs. So structurally speaking, composition, use strong types, value types, fold expressions, sum types, separate and compose, make generic implementations, and use RAII to your advantage. And if you use constructs which are declarative, if your code compiles, your code works. That's it from me for today. Thank you so much.